Alrighty, howdy folks. We are moving on to chapter 3. Okay, we're done with chapter 2. And so in chapter 3, let's pick up section 1. And here is the idea. Up until now, we were trying to find derivatives by applying the definition, right? For example, if we are supposed to find the derivative of f of x equals x squared, then we said, okay, what is f of x plus h? F of x plus h would be x plus h, the quantity square. And then we said limit of f of x plus h minus f of x over h as h approaches 0. And so that was a fairly long process to figure out just that limit and the derivative, right? That's not what we would always do. So here is an idea. So from now on, we will come up with some formulas and some derivatives that you just have to memorize. Okay? All right, without much further ado. For example, the first one is d dx of c is 0. That means the derivative of a constant is 0. Now the thing is, you don't need to take my word for it. You have to prove to yourself that this is in fact true. And turns out the proof of something like this is very simple. Here we are saying f of x is c. So if f of x is c, what is f of x plus h? That would also be equal to c. Do you agree with me? If I say f of x is equal to c, then f of anything would equal c. F of 5 would be c. F of 3 would be c. F of negative 10 would be c. So f of x plus h would also be c in that case. So that means f of x plus h minus f of x would be c minus c, which is 0. 0 over h. The limit is 0. You see? I mean, I'm sorry, I'm not writing all of these things down, but take a look at the textbook if you want to, just to satisfy your curiosity. For me, the more important thing at this point of time is that the derivative of a constant is automatically 0. Okay? All right. So based on that, could I ask a simple, silly question? Hey, what's d dx of 7, man? And obviously, it's like 7 is a constant, so the derivative is 0. Okay, can I get a little tricky on you? What's d dx of pi? What? Wait a minute. Is pi a constant? Of course it is a constant. It is some irrational number, 3.1415, it goes on. But it is a constant, so that's also equal to 0. Cool. Then, what is d dx of x? That turns out to be 1. Again, you can prove it. X plus h minus x is just h. H over h is equal to 1. Limit is equal to 1. So therefore, the derivative equals 1. Right. The next is a very important one, and it's called the power rule. It says d dx of x to the n is nx to the n minus 1 for all real. This is a fancy way of saying n is a real number. N is an element of the real number set. That's how you read it. N is in R, or n is an element of R is what you say. That's just simply saying n is a real number. That means any number between negative infinity and positive infinity. So in that case, the derivative of, when n is any real number, the derivative of x to the n is n x to the n minus 1. You must memorize this. Okay? Let me apply it and give an example. Can you, based on that, figure out what d dx of x to the 5 would be? Is this in the form of x to the n? Is x to the 5 in the form of x to the n? Yep. What is n? 5. So according to this, what should it be? What should the derivative be? 5 times n times, so 5 times x to the 5 minus 1. Did you agree? Okay, what is 5 minus 1? 4. So this just became 5x to the 4. So what is d dx of x to the 5? 5x to the 4. As simple as that. Cool. What then? There is this thing, d dx of c times f of x. Whoa, Nelly, this is wrong. Oh, this is big time wrong. Let me fix it right away. ZZ DO, come on, Sammy. C times d over dx of that's what this is. Man, I apologize for my big mistake there. Let me save this guy. Sorry about that. And go here. ddx of, where were we? This guy. So d dx of c times f of x is c times d dx of f of x. So this is what is called the constant multiple rule. That's because when you have c times f of x, we say c is a constant multiple of f of x. Right? It's a constant which is multiplying this quantity f of x. So c times f of x. When you have something like that, you can pull that constant multiple outside of the derivative and say c times d dx of f of x. That's what this is saying. Okay, so let me give examples. D dx of 3 times x to the 8.2. Does that look like d dx of some constant times a function of x? Yep, what is that constant c in our case? 3. Good. So, as a first step, can I pull that constant outside of the derivative? Yes. So, it becomes 3 times d dx of x to the 8.2. Right? Cool. Now, what is d dx of x to the 8.2? Did we learn anything about how to solve something like this? Yep, 3. It says d dx of x to the n is an x to the n minus 1. N is a real number. Is 8.2 a real number? It is. So, what's the derivative? 3 times. Something is so seriously wrong with me. Golly. What about the 8.2, man? So 3 times the quantity 8.2 times x to the 8.2 minus 1. Golly, that's 24.6. So this, adjust the size. Man, I apologize for wasting your time, guys. I'm so sorry. Hopefully I didn't make any more mistakes like this. Oh, crud. All right. So 3 times d dx of x to the 8.2. So 3 times 8.2, the nx to the n minus 1. 3 times 8.2 times x to the 8.2 minus 1. And that turns out to be 24.6 x to the 7.2. Cool? All right. And this is the derivative of a sum or difference is the sum or difference of the derivatives. That's how you kind of say this. If you are planning to find the derivative of a sum, that means the derivative of some f of x plus g of x, this one is saying, guess what? You could just find the derivative of f of x and find the derivative of g of x separately and add them up. That's what the sum or difference rule is saying. Similarly, for difference, if you're subtracting, you can subtract the derivatives. Cool? Do I have example? Yep. Can we apply the sum rule, sum difference rule? Yep, the derivative of this should be derivative of the first function plus the derivative of the second function. And the derivative of the first function is ddx of x is 1. ddx of x squared, apply the power rule, 2 times x to the 2 minus 1 or just 2x. You're beginning to get a hang of this? So you just memorize the rule and then start applying it to different problems. That's the whole idea. And the next one is the derivative of e to the x is just e to the x. There's a proof for this, but I'm not going to do all of that. Trust me, you just say d dx, the derivative of e to the x with respect to x is e to the x. What is e? E is that Euler number, which in fact is the limit of 1 plus 1 over x as x to the x as x approaches infinity. That's sort of the definition of, or rather where it came from, is based on this limit. And you learned about this one as the base of a natural log, right? That base of natural log is e. So the derivative of e to the x turns out to be just e to the x. This is another important result that you need to memorize. Cool? So take a good look at all these formulas, and this is what we're going to apply for the next few problems. What is d dx of 3 to the 1.92? Can we apply the power rule to it? No. What? That looks like x to the 1.92, man. No, man. Is the base an x, a variable x? No, the base is a constant 3. So 3 raised to a constant, that is still a constant, and the derivative of a constant is 0. See how I tricked you? So people will try to trick you on these kinds of questions. So please be very careful about that. Okay. Next. What is d dx of x to the 1.92? Oh, now we have the power rule, right? X to the n, which is 1.92 times x to the 1.92 minus 1, which is 1.92x to the 0.92. Cool? All right. Memorize the result of the problem. Ooh. What is d dx of square root of x? Square root of x? I have no idea. Well, you do. Do you know how to find this one then? Using, these, not the definition, but just the formulas. Can we use power rule on this one? By first writing this as x to the 1/2? That's the idea. Oh, now is 1/2 a real number? Yes. Do we have x raised to a real number? Yes. So 1/2 nx to the n minus 1 becomes 1/2 x to the 1/2 minus 1. But 1/2 minus 1 is negative 1/2. So we have 1/2 x raised to negative 1/2. But x to the negative 1/2 is 1 over x to the positive 1/2. Do you agree with that? Let me repeat that. X to the negative 1/2 is the same as 1 over x to the positive 1/2. So we have 1/2 times 1 over x to the positive 1/2. Cool. What does x to the positive 1/2 mean? Oh, that's the same as square root of x. Right? So I replaced x to the 1/2 with the square root of x. I hope you're following the logic. So what did it turn out to be? d dx of square root of x is 1 over 2 square root of x. 1 over the quantity 2 square root of x. You must memorize this because this particular one keeps coming in many places. Of course, if you forget, you can always resort to this technique, or write that x to square root of x as x to the 1/2 and go through all these steps. But my advice is just go ahead and memorize it, but be sure to know exactly how to derive it if somebody should challenge you. Cool? In the same way, there is another problem, the result of which I would like you to memorize. And that is the derivative of 1 over x. Do we know techniques of solving this one? Yeah, we can write 1 over x as x to the -1, right? Cool. When we do that, then this is looking like x to the n, where n is a real number. In this case, n is equal to -1. So applying the power rule, n x to the n minus 1, we get -1 times x to the -1 minus 1. But -1 minus 1 is -2. So this simply became -1 times x to the -2, or negative x to the -2. But x to the -2 is the same as 1 over x to the positive 2. Right? So we have -1 over x squared. So the result is d dx of 1 over x is -1 over x squared. d dx of square root of x is 1 over 2 square root of x. d dx of 1 over x is -1 over x squared. Please memorize. Cool. Wait a minute. That looks very complicated, man. Yeah, it does. But could we be clever about this one? Can we split this into two fractions? 5th root of x over x minus 9x to e to the x over x. Right? Yeah. And when we do, we have x to the 1/5 over x is x to the 1/5 minus 1. And 9x e to the x over x, x's cancel and simply becomes 9e to the x. Cool. So we have d dx of x to the -4/5. What did I do here? We were supposed to compute the derivative of the difference. Now notice what I did. Are we allowed to do that? Yeah, of course we are. The derivative of a difference is equal to difference of the derivatives. That means the derivative of the first function minus the derivative of the second function. Right? And so we have -4/5 x to the -4/5 minus 1 is the derivative of the first term. Constant multiple 9 I can pull outside. Are you paying attention? Constant multiple 9 I can pull outside of the derivative and simply say 9 times d dx of e to the x. But we learned that d dx of e to the x is just e to the x. So that's where I got this 9e to the x from. Cool. Now let's simplify this. -4/5 x to the -4/5 minus 1 is -9/5. So we got this. And if you want, we can write this as -4/5 times 1 over x to the +9/5. What does that mean? X to the +9/5? That means 5th root of x to the 9. I wish this thing rendered it differently. Microsoft equation, and 5 should have been written here. inside that, just slightly above that radical thing, that V looking thing. But anyway, so that's fifth root of 1 over x to the 9, negative 4%. All right. Next, what about this guy? Do we have a derivative of a sum? Is that the sum of the derivatives? That means the derivative of the first function plus the derivative of the second function? Yep, it is. Cool. What's the derivative of the first function? Does it look like ddx of x to the n? N is a real number? Yep. So 7.3 x to the 7.3 minus 1. That should take care of the first one. Cool. ddx of e to the 7.3. What do you think the derivative of e to the 7.3 is? Did we do a problem here? ddx of 9e to the x? Is this kind of like that? Or by some chance have you fallen into the trap once again? What? What trap, man? Well, is e a constant? Yep. Is 7.3 a constant? Yep. E to the 7.3, is that a constant? Yep. So the derivative of a constant is 0. Right? So that's the idea. So 7.3x to the 7.3 minus 1 plus 0. And that's just 7.3 x to the 6.3. Cool? All right. Ooh, I like these. ddx of e to the x plus 3 plus the quantity pi to the 3.1. Okay. Is the derivative of a sum? Yep, let's recognize that and say must be the derivative of the first one. What happened to the equal sign, man? Oh, brother. So ddx of e to the x plus 3. How do we find ddx of e to the x plus 3? Recall, a to the m plus n is a to the m times a to the n. Why did I say that? What has that got to do with this problem? Everything. Does this look like a to the m plus n? This e to the x plus 3? Yep. So how can we write this? E to the x times e to the 3. You agree with that? So let's do that. And okay, that equal sign should have been here. I'll fix it in just a second. Yeah, maybe I'll go ahead. There we go. Alrighty. So a to the m plus n. So we can write this as ddx of e to the x times e cube. But then what is ddx of pi to the 3.1? Again, that's a trick question, right? Pi is a constant. Pi raised to 3.1 is just a constant. So the derivative must be 0. Cool. Now, is e cube a constant that is multiplying e to the x? So can we pull this constant outside? Yep. So that simply becomes e cube times the ddx of e to the x. But ddx of e to the x is e to the x. So e cube times e to the x. But then we can put this back together and say e to the 3 plus x. Because as you can see here, a to the m times a to the n is a to the m plus n. The thing is, over here, we needed to split e to the x plus 3 as e to the x times e to e cube. But then when we got the answer, we could have left it like this, but then I just wanted to show you that we could add the exponents and write this as e to the 3 plus x. If you don't do that, you just leave it as e cubed times e to the x, I'll still give you full credit in a test or something. But if it is the Weber sign, oh, it doesn't recognize this, then, I just want to show you, if that were to happen, what it is that you need to do. Cool? I think that's it. So from my side, there are not a whole lot of problems that I can show you. In a sense, it's up to you to now take paper and pen or pencil and start working problems out. I have explained pretty much everything that I needed to explain from my side. All right, folks. With that, I think I'm going to move on to the next one, which is chapter 3, section 2. Come on. I thought I already had it open, but looks like I closed it. All right, let's get busy. Oh, just 4 slides. Very nice and interesting things. The product and quotient rules. So this is 3.2, chapter 3, section 2. And here is the main idea. Before I mention this, is the derivative of a sum equal to sum of the derivatives? That means derivative of 2 things are adding. Could I take the derivative of each one of them and add them up? Yep. Does multiplication work the same way? The answer is a big time no. Derivative of f of x times g of x is not equal to, big time not equal to, the derivative of f of x times the derivative of g of x. Nope. Instead, it is the first function f of x times the derivative of the second function plus the second function g of x times the derivative of the first function. There's a nice proof of it if you are interested, but I'm going to skip the proof. But here is the idea. First function times the derivative of the second function plus second function times the derivative of the first function. That's product rule. Quotient rule. Let's look at this one. That looks a bit complicated, but my hope is that you keep writing this formula over and over again every time you use it, that it becomes second nature to you. Did you hear me say that? The best, you must memorize these things. And one good way of really memorizing it is, not only do you memorize it, whenever you're doing a problem, every single time, just write down the rule. Hey, I'm applying the product rule. ddx of f of x times g of x equals f of x times g prime of x plus g of x times f prime of x. Or say it out loud for yourself. Cool. What is ddx of f of x over g of x? It is g of x is the denominator times the derivative of the numerator minus numerator times the derivative of the denominator all over the square of the denominator. Cool? This is the quotient rule. And some people remember this as low d high minus high d low over low low. And I had a student long time back. That guy, he didn't know much at all in calculus. But one thing he knew was this quotient rule. So every time I would look at him and say, I needed to apply quotient rule, I would ask him, hey, what's the quotient rule, man? And he had a beautiful deep bass voice. And he would say, Lodi ha minus Hattie low over low low. Every one of us, we got a big kick out of that. So, folks, what's the quotient rule? Lodi ha minus Hattie low over low low. What does it mean? Low means the denominator, L-O-W, low, right? D high means the derivative of the high is the top. Denominator times the derivative of the numerator minus high numerator, D low derivative of the denominator, all over low denominator square, right? Denominator times denominator. That's the idea. So that's how the quotient rule works. Lodi had minus had low over low. All right. Let's look at this guy. What do we seem to have? Do we seem to have a product here? Something times something? Yeah, we have ddx of f of x times g of x. Cool. So, is it time to apply the quotient rule? Product rule? First function times the derivative of the second function plus second function times the derivative of the first function. That's exactly what I'm about to do. First function times the derivative of the second function plus second function times the derivative of the first function. So this, you don't do anything. Leave it as x minus square root of x. But then the derivative of x is 1. The derivative of square root of x is 1 over 2 square root of x. Right? That's one that we needed to memorize. And so we got that. And similarly, x plus square root of x times derivative of x is 1 minus derivative of square root of x is 1 over 2 square root of x. Cool. Now, if we FOIL this out, x times x times 1 is x, x plus 1, x times 1 over 2 square root of x. What? Yeah. Would you agree square root of x over square root of x is just square root of x? What? X over square root of x, isn't that just square root of x? Yep, it is. How did you get that? Well, there are two ways of doing it. Maybe one way. Let me show you. Can you write what is square root of x times square root of x? Isn't that just x? So, if I write that x like that, now aren't we left with just square root of x? That's the idea. Or you can say x over square root of x is x over x to the 1/2, and that becomes x to the 1 minus 1/2, which is x to the 1/2, and that's square root of x. So you can use either one of these methods to arrive at that result. Okay, so I FOILed everything out, and then I notice that, wait a minute, there's a 1/2 square root of x, and there's a minus 1/2 square root of x. That add up to, those things add up to 0. And negative square root of x plus square root of x adds up to 0. And then we have an x plus x is 2x, and minus 1/2 plus minus 1/2 is negative 1. So that just reduces to 2x minus 1. Cool? So I applied product rule to solve this problem. But I have a feeling at least some of you just went, hey, wait a minute. Why did you do all of this, man? And couldn't you have simplified the original problem? Did anybody think that? If you did, you gotta pat yourself in the back. So here is what I'm talking about. There's a method 2 to this one, which is, what does this look like? X minus square root of x times x plus square root of x. Does that look like a minus b times a plus b? Yep, a minus b times a plus b. What is that? Difference of squares formula. That's equal to a square minus b square. So guess what? That's just x square minus square root of x. When you square it, you just get x. Right? And now, this is the derivative of the first term minus the derivative of the second term. X squared, the derivative is 2x. Derivative of x is just 1. How simple this became. See? So, I wanted to show you that sometimes simplifying actually helps you a lot. So, how should you do it? If you were given this problem, I don't care which way you do it. I mean, you're showing that you're pretty clever by doing method 2, and I think I would be impressed by that. But if you could not think of it for some reason, you just wanted to use brute force and go through this, yeah, that's okay. All right. Next. Whoa. One look at it. What rules it appears that we need to be using? Do we have f of x over g of x? Right? So that means quotient rule. Low d high minus high d low over low low. So let's get busy. Wow. Denominator, low, times the derivative of the top. So the derivative of x cube e to the x. Any idea what that should be? What am I asking? What's the derivative of x cube e to the x? Do not say derivative of x cube times derivative of e to the x. That would be an egregious blunder. We have to apply product rule. That is, first function x cube times the derivative of the second function e to the x plus second function e to the x times the derivative of the first function. So we say 1 over x plus e to the x, the denominator, just copied it, times, I applied the product rule, x cube, first function, times the derivative of the second function, plus second function, times the derivative of the first function. Notice how patiently I'm just writing it down. I'm in no hurry sometimes because I don't want to make any mistakes. So patiently I write down everything. Cool. Minus high d low top x cube e to the x numerator times the derivative of the denominator. I didn't even figure out what the derivative of the denominator is. Just wrote down derivative of the denominator over the square of the denominator. Cool. On purpose I picked a slightly harder problem. I could have picked something like derivative of, hey, what's ddx of x over e to the x, right? But I did not. Here is the idea. So x cube, what is ddx of e to the x? E to the x. What is ddx of x cube? 3x square. That's exactly what I wrote. What is ddx of 1 over x? I asked you to memorize this. Negative 1 over x square. ddx of e to the x? E to the x. So this is what we have. So let's see if we can distribute this out. And when you do, 1 over x times x cube e to the x becomes x square e to the x. And this becomes 3x e to the x. Okay. Minus times minus is plus. So that becomes... what? Oh no. I have e to the x times x cube e to the x. So that is x cube. What will it be? E to the x times x cube e to the x. I seem to be saying that's x cubed e to the 2x. Is that right? Yeah. What is e to the x times e to the x? Does that look like a to the m times a to the n, which is a to the m plus n? So shouldn't this be e to the x plus x? X plus x is 2x. So e to the 2x. That's where I got the e to the 2x from. Okay. And then e to the x times e to the x is e to the 2x times 3x squared, which is what I wrote here. Minus this thing times the negative, that becomes plus, minus a negative becomes an addition. And x square reduces to x cube over x square reduces to x, and that's what you see here, e to the x, right? Minus x cube e to the x. Be sure to distribute this negative to this term as well. So minus x cube e to the 2x. Okay. And then see if we can simplify this. There's an x square e to the x, 3x e to the x, but there is an x e to the x here. So that adds up to 4x e to the x. And then there is an x cube e to the 2x here, but there is a negative x cube e to the 2x. They add up to 0. 3x square e to the 2x is what is left. Right? Whoa, man, that is pretty big. Welcome to college. That's all I can say. You'll be dealing with stuff that is much more complicated than this. So get used to it. Be patient. Take a good long piece of paper and work everything out where there is clarity, so that you yourself understand. You got to proceed in a logical fashion, making sure you write down everything. Get used to that way of solving problems, and that will help you a lot. Okay. Whoa. Looks like I didn't even stop there. Wow. Okay. Just looking at x's. There's an x square, there's an x and an x square. Can we factor out an x? It's e to the x, e to the x, e to the x, e to the 2x. You can factor out x e to the x. That's what I did. Which means we'll be left with an x from here, for 4 here, and 3x e to the x from this one. And I wrote like that. I'm thinking, is there any other way to simplify this? Boy, you could multiply both the top and the bottom by x square. So that would cause this to disappear. Anyway, this should be good enough. Whoa, find dy dx and d square y dx square. I talked about what a second derivative is earlier. So looks like this time we are being asked to find a second derivative as well as the first one. Okay, let's see. Let's get busy. Dy dx is ddx of y, right? Dy dx is nothing but ddx of the quantity y. But what is y? Oh, y is x over x squared minus 1. So ddx of that quantity. Cool. How do we find this derivative? Quotient rule. Low d high minus high d low over low low. X squared minus 1, the denominator, times the derivative of the numerator, minus numerator times the derivative of the denominator over the square of the denominator. Right? And that turns out, when you simplify, negative x squared minus 1 over this. Cool. And now if you want to find the second derivative, what did I do? Oh, I just multiplied this out. Okay. And to find the second derivative, the way it works is, second derivative is nothing but the derivative of the first derivative. Please pay attention to that. Second derivative is the first derivative of the first derivative, or rather the derivative of the first derivative. So d dx of, I'm replacing the dy dx that we got here. Okay. Now, that's going to be again a quotient rule, right? The numerator times the derivative of the denominator minus, what did I say? Denominator times the derivative of the numerator. Wow. Wake up, man. Come on. I'm sorry, folks. So denominator times the derivative of the numerator minus numerator times the derivative of the denominator. That's exactly what I did here, over the square of this. Cool. Now simplify it and all that stuff. There's something I want to mention here though. Okay, I simplified all of that and finally factored things out, and I'm sure you can follow the algebra here. But there's one point that I want to mention here clearly. When I got to this step, as I was doing the video thing, I stopped here. But then I didn't realize when I moved to the next one, I had this thing. How come I just didn't leave it as x squared minus 1, the quantity square, in the denominator? Well, the thing is, please pay attention to this. If we were supposed to find just the first derivative and you said this is the answer, done. There's nothing else that needs to be done. There was no need to move into this step. However, we were asked to find the derivative again, the second derivative. But the thing is, we don't know how to differentiate x squared minus 1, the quantity square. In the low d high thing, right? We need the derivative of the denominator. But when the denominator is written this way, we don't know how to differentiate that. X squared minus 1, the quantity square. Nope. Unless we expand this out and write as x to the 4 minus 2x squared plus 1. That we know how to differentiate. And it is because of that I went ahead with this step here, okay, which is what helped us in this problem. So here, notice we needed the derivative of the denominator, which is this guy, 4x cubed minus 4x squared. X cubed minus 4x squared. Jeez. That should just be 4x. The derivative of 2x squared is 4x. Golly. Man. I hate making mistakes because it's not fair to you guys. I mean, you're already having a hard time with the concept, learning all the concept as it is. And if I come and start making things more difficult for you, that just is not right. So minus x plus 4x to the 5 is fine. And this changes to 4x cubed. Brother. So this would be wrong. Yeah, I'll ask you to simplify this. Okay, the main concept is the derivative part, and if I goofed here, I'll try to fix it. And when I post the notes, the video, unfortunately, I cannot record the whole thing back again. But when I post the notes, I'll make all the corrections that I need to make. Okay, folks, that's it. Please forgive me for the mistakes that I have made. I assure you, I am not infallible. I do make mistakes, and I hope you have the heart to forgive.